In this installment of our study of microcontrollers, we consider the programming aspect of working with the Arduino Nano. Up until now, the only sketch or Arduino code that we've examined is the Blink sketch. We're going to take a look at it again in a slightly different form, and I'll point out the important differences from what we saw before as we go. First, let's define the word algorithm. An algorithm is just a set of clear step-by-step instructions, like a recipe in a cookbook, or a set of instructions for assembling a piece of furniture you bought from someplace like IKEA. Computers need well-defined sequences of instructions in order to carry out tasks, so algorithm development is necessary in order to make computers work properly, that is, to make them do what we want them to do. Now let's look at the Blink sketch. The most important difference between the Blink sketch we dealt with before and this one is that this one doesn't use the defined term built in at all. Instead, the term LED is defined right off the bat. It's the first instruction, and the arrow points to it. In fact, this sketch is structured so that it begins with the definition of the term LED, which is set equal to 13. The int in front means that the term LED has to be an integer. This is the syntax of a term that we define in the Arduino language. First, there's the term type, here an integer. Then the term name, here LED is the word that we've chosen to represent the term, and then what its value is. After definitions, and there could be several, but in this sketch there's only one, we have the setup function. And this is followed by the loop function. There are some characteristics of the IDE that make it easier to create, modify, and debug sketches, such as the highlighting of parentheses and bracket pairs. Additionally, some text is colored, and this reminds us of the special roles that such text play. Some words have fixed definitions or values, and we aren't allowed to change them. These are called constants, and they are marked in blue. Examples here include output, high, and low. Then there are data types, such as integer. This is shown in the definition of the term LED, where it's written in orange as int. Then there are functions, which are used to control the Arduino board and to perform computations. These are also written in orange, and they include arguments that are contained in parentheses. What sort of arguments these are and how many there are depends on the function. Examples in this sketch include the function delay, which takes one argument, and digital write, which takes two arguments. Lastly, there are structures, which are elements of Arduino code that control and direct the flow of computation. Examples in this sketch include the loop. This is a structure that does exactly what its name indicates. It executes in turn each of the commands contained in the brackets, and then it repeats the sequence of commands again indefinitely. For more information on the various classes of elements and complete descriptions of all constants, functions, and structures that are part of the Arduino language, go to the link that's listed here. Now let's talk about variables. A variable is a place which we can think of as a bucket where a piece of information can be stored. There are several types. For example, integers, abbreviated int, like the variable LED that is defined at the beginning of this Blink sketch. Real or floating point numbers, specified using the word float. Boolean variables, named after George Boole, 19th century mathematician who made many contributions to the field of mathematical logic. A Boolean variable's value can be either true or false. The key word used is bool. And then there are variables whose values are strings or sequences of characters. Such variables are defined using the keyword char or char. A variable has to be declared before it can be used. As we see in the sketch, the syntax of a variable declaration is shown in setting up the variable LED. The command begins with the variable type, int, followed by the name of the variable, then an equal sign and the number 13. This indicates that the variable LED is an integer whose initial value is 13. The name of a variable can't already be used by something else. It must be unique. If it is declared outside a function or other structure, as is the case with the variable LED here, It is called a global variable and can be used within any function, anywhere in the sketch. If it is declared within a function, it can only be used within that function. Here, LED is used in both the setup and in the loop functions, in two places. Now let's consider some algorithms. Suppose I want to develop an algorithm to brush my teeth. I'm going to start by making a flowchart. So the flowchart is a way for me to lay out the logic step by step of what I want to do using words. Okay, the first box is the start box. We always begin there. And that leads to the first step, which is I need to find my toothbrush. So each of the steps that I undertake is going to be shown in a box, and the flow is shown with arrows directing from one step to the next. The next step is I put toothpaste on the toothbrush. Then I brush my teeth. Then I rinse the toothbrush with water. Then I put the toothbrush away. And then I'm done. Note that these instructions are a sequence, one step leading to the next. At each step, there is only one possible next step. This is straightforward, but it doesn't take advantage of all the power and capability of a computer. So let's look at something a little more complicated. Let's consider a control structure that involves decision making. We will analyze the if structure shown here on the left. We see that after the if, there is a statement enclosed in parentheses, and that it's followed by some number of commands enclosed in curly braces. These commands only execute if the statement inside the curly braces is true. So the first thing that has to happen is that the statement has to be evaluated to determine its veracity. It's either verified or a comparison is performed. Which comparison the comparison that's performed is determined by the operator. Here is a list of operators that can be used within the Arduino language. Note that when we're trying to determine whether two things, here thing 1 and thing 2, are equal, we use two consecutive equal signs to represent that. The rest of the operators are not difficult to understand, even the not equal operator, which is the exclamation point followed by an equal sign. The exclamation point is often pronounced bang. Here's an example of the use of the if control structure using verification. We declare the Boolean variable called light on and set it equal to true. Later, light on is enclosed in parentheses in the if structure. This means that its value is checked. If light on equals true, then commands 1 and 2 are executed. If it's false, then the commands inside the curly braces are skipped. Here's another example. Here, we initially declare the variable LED1 to be an integer with an initial value of 13. In the following if control structure, the statement LED1 does not equal 13 is tested for veracity. According to the variable declaration, LED does in fact equal 13, which would make the statement false. And that in turn means that the commands inside the curly braces are not executed. Both these examples, along with the original definition at the top, are examples of pseudocode. Pseudo means fake. The examples all have the structure of code with the parentheses, braces, and semicolons in the right place and with variables declared properly. But you'll notice that the commands that are listed here, command 1, command 2, command 3, are not true commands. They're enclosed in double arrows. They're just placeholders for real commands or real functions that you would use. Pseudocode is code-like, and writing it is an intermediate step between creating a flowchart and writing true executable Arduino code. So speaking of flowcharts, let's create one that helps us decide whether or not to carry an umbrella when leaving the house. We start with start, followed by the arrow showing the next step. So the first thing we want to do after starting is check the weather. Then the next step is we ask the question, is it raining? Okay. If the answer is no, it's not raining, then we're done. We can just leave the house. If the answer is yes, then we have to take an umbrella and then leave the house. So you'll see that the question, raining, is enclosed in a diamond-shaped box. And this is a decision point. There are two arrows that leave the raining box. And the direction of the flow depends on the answer to the question. This is expressed, coded, using the if statement, or the if control structure. And here's the pseudocode that corresponds to it. The statement that's tested is if the weather is equal to raining. Let's look at another example. This time, we're interested in carrying out the task of putting on shoes. The first step is to find shoes. The next step is to choose a shoe to put on. Presumably, we have a pair. The question is the shoe the left shoe? If the answer is yes, it is, we put it on. And then we put on the right shoe. And then we're done. We put on our shoes. But it's possible that the shoe that we picked up was not the left shoe. It was the right shoe, so we put that on. And then we take up the other shoe. It's the left shoe. We put that on, and then we're done. So either path leads to the desired result that we have shoes on. And this is a case where we have different tasks that are completed depending on which path we take. So this is a case where we want to have options. Okay? We have one path with if the statement is true, and that's the yes path, the left shoe. Okay? And then the other is we follow a different path. And the control structure that we use here is called the if-else structure. And here's some pseudocode that corresponds to this. So we have the statement that we test is the shoe the left shoe. If it's true, we carry out the commands within the curly braces that immediately follow. And then we can put else after that, which is what is executed if the statement at the top, right after the if, is false. Here's another example. Let's say we want to write a flowchart and develop an algorithm for washing our hands. We start, and the first step is to turn on the water faucet, followed by rinsing hands. Then the question is, are our hands clean? If they're not, we have to apply soap to our hands. And then we scrub them. And then we rinse them. And then we check again. Are our hands clean? If the answer is no, then we apply soap, scrub the hands, and rinse them again. And we just keep doing that. We keep doing that. This is a loop, and we keep looping back until it's the case that our hands are clean. And when they are, we're done. This kind of algorithm can be implemented using a while loop. And this is the structure of a while loop. While a certain statement is true, carry out these commands. In this particular task, the pseudocode for carrying it out is here. The statement that needs to be true in order for the while loop to execute is that our hands are not clean. So it's coded like this: hand status not equal to clean. And again, this is all pseudocode. It's code-like, but these are not real commands. There is no variable that we've set up called hand status. There's no variable we've set up called clean. We haven't written actual functions to do these other things, but this is to give you an idea of what structure you would need to implement to make this happen. Now, here's another one. Let's say that the task this time is we want to eat a dozen eggs. First thing we want to do is make sure we have a dozen eggs. So let's buy some eggs. We buy a dozen eggs. Next is we set the number of eggs that have actually already been consumed to 0 because we haven't eaten any of them yet. Then we eat 1 egg. Then we increase the total number of eggs eaten by 1. And this tells you that we have a counter that's involved here, okay, where we're keeping track of how many eggs that we've already eaten. Then comes the question, have 12 eggs been eaten yet? If the answer is no, then we go back and eat an egg, and then increase the total number of eggs by 1, and then check that total again. And we keep doing this until we actually reach 12. All 12 eggs that we bought have been eaten, and then we're done. So this is another loop. You can see how there's looping back, but this one is one that involves a counter. And here is the structure that we need. This is called a for loop, and within the parentheses, we don't just have a statement that we test for veracity, we have other stuff in here. Here's how we would structure this, the pseudocode that we would use to set this up. And actually, everything in the parentheses is really what we would put in. We can set up a counter. It's a variable that we use just within the for loop. We've declared it here. It's an integer. It's an index that's set initially to 0 and that we're going to increment. And while its value is less than 12, the I++ means increment by 1. Okay, so the statement that we test is I less than 12. Is that true? If it's true, then carry out the instructions within the curly braces. And the only instruction here is eat an egg. That is the pseudocode, but as I say, the actual stuff in the parens is truly code. So now all these different control structures are very powerful and you can do a lot with them. Lots of algorithms can be developed, and so I would like you to develop an algorithm for accomplishing a task, a basic task, similar to the ones that shown in these examples, and I'd like you to come up with both a flowchart and pseudocode for it. You can choose any one of these tasks to carry out. You can choose a different task if you wish, but you have to get permission from me to actually do that task and develop the flowchart and pseudocode. The idea is that you should develop an algorithm that contains at least 6 steps, and that's not including the start and end step. It should have at least one decision box. It could have a loop in it. It does not have to have a loop, but it could. Okay, so you need to have at least one of those things. There is a due date for this assignment that's been posted on Canvas, and I would like you to handwrite this assignment and turn it in on loose leaf paper. So that's an assignment for this to follow up on this information about algorithms and pseudocode. So now let's change gears a little bit and start looking back at the Nano again. So here is the board, and we've already looked at some of the pins on this board. We've dealt with D13. That's the pin on the Nano that's associated with the LED on top of the board that blinks, and that's the one we can connect and implement the blink sketch that's preloaded on your Nano, available in the Arduino IDE, places like that. It's very accessible. It's already written, assuming that you want to use pin 13. That's a digital pin. There are some other digital pins too, though, here. In fact, D2 to D12 is on those pins are on the other side of the board. And then you'll see some other pins that I've marked here. So what does this mean? When something's digital, it means that it has 2 possible settings, on and off. So on here is represented using high, and we've already seen this in the blink sketch, and this corresponds to 5 volts. Basically, what you get at a pin is a voltage. You can measure the voltage at any one of the pins. So if you set a pin to be high, it's going to be nominally 5 volts. If it's off, it's nominally 0 volts. And those are the only values that you're going to see at these digital pins. Now the analog pins, analog means you can have a number of values, really any value along a continuum within a range. And again, the range is going to be probably 0 to 5 volts, but the voltage could be anywhere in between that. And those pins are marked A1 to A7. So we've already done some stuff with this in the blink sketch. The first thing we do is we select a pin and we decide whether it's going to be an input pin or an output pin. Now you'll see here that pin 10, in this case we're talking about pin D10, is set up to be an output pin. And that means that we're going to set the voltage there. We want to specify that that's a pin where we set voltage, and then later on we can write the voltage. It's later on in the sketch. So to do the digital write, we are saying this is a digital pin. We want to specify the voltage there, and it can be set to either high or low. So we have to give the pin number and then whether it's high or low. When we use digital pins, we just include the number. We don't put the D in front. So that's digital write, and that's setting the pin to output mode. It's also possible to have one of these pins set to input mode, and in that case we would be measuring what the voltage happened to be there, not dictating what it would be, finding out what it is. So in order to do that, if you look at the code that's down at the bottom of the screen, I want to draw your attention first to the line that's second from the bottom, and that's where we set the pin mode of pin 6, and that's D6, to input. Okay. And then what can we do with that? Well, we can read what the voltage is there using the function digital read. Now with digital read, there's only one argument, and that's the pin number. You're saying, I would like to know what the voltage is at that pin. And that's fine, but once you get that, you want to save that value, okay? And that's why we set up a variable called D6 value. I want to know what that value is, tell me what it is. I need to declare that variable, set aside that bucket where I want to put that information before I need to use it. So that's why I have int D6 value equals 0. I know this is going to be an integer because digital read has one of two values, high or low, or 0 or 5. So it's going to be 0 or 5. That's what it's going to be, a number. So I can set digital read once I've read the voltage there to this D6 value, and that way I capture that value, which I might want to use for something else. We have other functions for dealing with the analog pins that we'll learn about later. You'll notice also that there are 2 ground pins on the Nano. So knowing all this, we can actually create other circuits. The traffic light circuit that we've already looked at had one path where we attached to pin 13, D13, and then we attached a resistor and then the LED to it, and then we attached the cathode of the LED, the short leg, back to ground. But now we'd like to create a circuit where we have 3 LEDs, red, yellow, and green. And each of them has a 220 ohm resistor in series with it, and we need to attach them to different pins. So we have to select 3 digital pins. You can pick any 3 digital pins, and you want to set them up as output pins. Okay. So within the setup function, we have to set them up and indicate that those are output pins. And here's an example of one of the pins that you could set up that way. And then within the loop function, then we can write to them. So these are the basic tools that we want to use. One thing that I will say is when you set up this circuit, you're probably not going to want to choose 3 digital pins that are immediately next to each other, because you're going to have a lot of wires in close proximity to each other. It will be very crowded there. It might be better to spread them out a bit. And then you have to remember to be careful about how you lay out the circuit. You don't want to inadvertently put resistors, attach these resistors to each other. So make sure that the ends of the resistors and the ends of these LEDs do not actually sit in the same row as one of the other branches. The other thing we have to do is make a way so that all 3 of these paths can attach to the same ground pin. So that's going to mean that you're probably going to want to attach the cathode, the short leg of each of these LEDs, to the negative rail, the column that's on one side of your breadboard. And then from there, attach to ground. Just attach one wire to ground that serves for all 3. So now we have to consider building the traffic light circuit. That's the circuitry that we want to have. We want to have green, yellow, and red LEDs blink in succession. First thing you want to do is write an algorithm. And you can base it on the blank sketch. You can just modify it. Okay, you can take this version of it if you like. You can take the one that you have already. You just have to make sure that you specify all the LEDs that you need. You want to create the sketch, build the circuit, and you might want to consider simulating it in Tinkercad first, because when you do that and you make a mistake and it doesn't work, it's fine. You don't have to worry about frying any components, including the board. Then you want to take your sketch once you get it working. You want to upload it to the Nano and test it to make sure that it works. Once it works, I would like you to take the sketch and upload it to Canvas. So here are the paths that where you will find your sketch based on what utility you use to create the sketch. If you use the Arduino IDE, this is the path where you'll find it. Now, sketch name is going to be whatever you name it. Okay, it's going to be in its own directory, and then it's going to be the sketch name, whatever it is, .ino. If you use Tinkercad, there's a download capability, and you can download the sketch onto your computer, and then you can just upload it from there. There is an accompanying video that talks about how to make these INO files and how to manage them that you'll find that I've provided a link for. So you can look at that and see the specifics for that. So you need to upload this sketch to Canvas. And then I ask that you bring a working circuit to class so that I can check it, and you can show me how it works.